This is number 11 for 2.6a. I'm just going to get you started here so you can kind of see where to go with it. I'm not going to finish it for you, but I'm going to get it started. So on number 11, your equation or your function is y equals x squared plus 1, which is a parabola. So I want to get a picture of that going for you. So let's do a little sketch here. You should do that also. This would have a vertex at 0, 1, and then it'd go through 1, 2, and 2, 5, etc. So the parabola looks like this. All right, and we were supposed to find a little dot here, the rate of change of a point P, and I'm just going to put it on here, right P here, and its distance from the origin as the x-coordinate is changing over time. And so what they tell you, I'm going to kind of go like this, is they tell you that this along the x-axis, which we call dx dt, they tell you that that's changing at a rate of 2, and I think it's centimeters per second. I'm not positive about that label. I don't have my book open right now, so I'm trying to remember this on the fly, but I believe it was 2 centimeters per second. And you're supposed to find how that's causing the rate of change of P from the origin. See, as I'm moving here, the distance of P from the origin is getting greater and greater too, and I'm trying to find the rate of change that that distance is moving. And I want to find it instantaneously, they say, at the point 2,5, meaning what's happening right here, instantaneously, what's its rate of change from the distance to the origin. So I'm going to connect this right here to the origin, and I'm going to call that D for its distance to the origin. So really what I've got here is I'm going to write P as coordinates. It'd be x comma x squared plus 1. And the origin is the point 0, 0. And my equation that I'm going to write is for D, the distance between the origin and point P. So I'm going to use the distance formula. And remember, your distance formula is x2 minus x1 squared plus y2 minus y1 squared from Algebra 1 and Algebra 2. So I'm going to take that and apply that formula to this situation over here. So my distance D can be found by doing the square root of, and I would do x minus x, which would be x minus 0, plus y minus y, which would be x squared plus 1, minus 0 squared. So that's what I've got when I use my distance formula. So my equation for D is going to look like x squared when I clean it up, plus, and I'm going to FOIL that out, which would give me x to the 4th plus 2x squared plus 1. I'm going to write FOIL on there. And again, I'm getting an equation for D because my goal is to find the rate of change of D with respect to time. So I want to find this. How fast, or what's the rate of change of my distance from the origin. So when I clean this up, I'm going to have x to the 4th plus 3x squared plus 1. This is an equation that models my length D to the origin. Now let's take a look and organize this into what we know and what we need to find. In this problem, they tell us that dx dt is 2 centimeters per second. So I know the rate of change of x with respect to time. They want me to find the rate of change of the distance from the origin with respect to time, and they want me to find it when P is at the point 2,5. What's the instantaneous rate of change, or the derivative, of the distance to the origin at the point 2,5? So now I'm ready to start the problem. I'm going to move this over here a little bit, and I'm going to write that in a form that's easier to differentiate. So I'm going to get myself an exponent. So there's my equation, which models D. I am looking for the rate of change of D with respect to time. So I'm going to take the derivative of both sides with respect to time. So the rate of change of my distance with respect to time will equal the rate of change of my distance function with respect to time. Again, I'm just doing the same thing to both sides. Now, I'm going to stop here for a second. We don't have a match here. I want to have you keep in mind what you're doing with your chain rule here. We're trying to find the rate of change of the distance with respect to time. So what we're going to do is we're going to do it with respect to x first. So we are going to do dx to the fourth plus 3x squared plus 1, it's rate of change with respect to x, and then we're going to do times dx dt, and we're going to have a chain going on. So the first thing I'm going to do is do this with respect to x. So I'm going to use my product rule, which says, and again, whenever you don't have a match of variables, time versus x, we have to do it with respect to x first. So I would have 1/2 x to the fourth plus 3x squared plus 1 to the negative 1/2. And then I have to do times the derivative of the inside, which would be 4x cubed, the power rule, plus 6x. And again, that's the derivative of my function with respect to x, which is what we did most of chapter 2. But I need to multiply that by dx dt. So, and I can't fit it on the screen, but here, I'm going to go like this. Dx dt will be going right behind that. So keep in mind what you've got going here. You're going to do the rest of the cleanup, but you know what dx dt is. It's 2 centimeters. So you're going to be putting a 2 centimeters in for dx dt. You're going to be cleaning this up, and they say to do that at the point 2, 5. So once you clean this thing up, you're going to plug in 2 for x, because that's what was given, and you are also going to plug in 2 for dx dt. And so if you go clean up this function and plug it in, you should get the answer that matches in the back of the book. I'm not going to finish the algebra off for you, but I want to explain again in detail what you're doing here. You have a point P, I'm going to go back over here, which is changing with respect to time. It's getting farther and farther and farther away from the origin, and they tell you the rate that the x is changing. They tell you they're having to go 2 centimeters per second, so about this fast, about 2 centimeters in a second. I'm going to move it at about that rate if I can get this going here. So about 2 centimeters per second. They want to know instantaneously, right there at the point 2, 5, what's the rate of change of its distance from the origin. So what I went and did is I found a formula or an equation for the distance from the origin. And I'm going to take its derivative with respect to time, which is what I did right here. And once I get it all cleaned up, I'm going to plug in the value of 2 for x, because that's where they told me to do it, instantaneously at the point 2, 5, and they told me the rate of change for dx dt. So that's done. I'm not going to finish the algebra. You can do that.